work with molecular materials, in this case with molecular dyes, because most of the time they have very high performing optical properties, and they allow a very good tunability of the optical properties. They generally show very high quantum yield of luminescence and high station coefficients. So they allow to work very well with them in different environments. And of course, you can also tune the properties by functionalizing them. But this is mainly true when we work in liquid solutions. Unfortunately, these liquid solutions are not so suitable for solid devices in which you want to work with polymeric and plastic materials. So if you want to go to the other side, you want to work with plastic or polymeric materials, you start having some problem, because the behavior of these dyes in the solid materials is not always the same as in the liquid solutions, because sometimes the matrix is inhibiting the optical properties because of the rigidity or because the low solubility of these dyes in this media. So there is this difference, and there are very typical examples that I show here briefly. So one example is the fluorescein, which we know is a very high fluorescent dye when it's in a water solution. But it becomes non-fluorescent when it's in its crystalline state because of aggregations. A similar effect, even if in the opposite direction, is that they show no fluorescence at all when they are dissolved in solution, but becomes very high fluorescent in the aggregate or rigid state. So these are two examples of monomolecular photophysical processes that show that the behavior of molecular dye can change dramatically when we go from the solid to the liquid state, or vice versa. But this is also happening even more in an accentuated way with multimolecular processes, because these usually are governed by diffusion of the molecule to proceed. So if we put these dyes in solid materials, diffusion is prevented, and this must be compensated by an increase of concentration of the dyes, which sometimes is not possible, or even increases the costs considerably. As example of these are fluorescence energy transfer, triplet annihilation, and so on. So our idea is to combine the best of the two worlds, the best properties that you have usually in solution, with the mechanical properties that the solid polymer materials provide. So to do this, we developed since the last years, during the last years, a few strategies based on encapsulations, which is basically based on this core shell capsule strategy, inspired by this chocolate liquor structure, where we have a core material which can be made by oil, wax, solvents, which is trapped within a polymeric shell, which is containing and protecting the inside liquid material. And of course, in the liquid material, you can dissolve your dyes with other additives like sensitizers or quenchers and so on. Now, you might have solid particles in their dry state, but inside each particle is a liquid solution. So you have solid materials that can behave like a liquid material. Now you can take these particles and embed them in a polymeric matrix that, even if it's rigid, is still allowing the liquid behavior of these dyes. And I'll show you later during this presentation that this strategy is quite simple. It is universal. It can be used for different and usually doesn't need to functionalize or chemically modify the dyes or the material, the polymer materials. So Here I show you some of the work that we have been doing by using this strategy. We managed to make thermochromic sensors, temperature responsive white emitting materials, up conversion in the solid state, and photochromic materials that work in the solid state like a liquid. For time reason, I'm just concentrating in this two example, hoping that it gives you an idea of the feasibility of the strategy. So I'm going to speak about photochromic materials now. A photochromic material, especially the T-type, are molecules that are able to absorb photons and switch from one form A to a form B, which usually has a different absorption properties. Now, this form gets, once you stop the light, turns back to the original state spontaneously or by radiating with a different frequency. Since we are working with molecular material, we focus on spirooxazines, spiropyrans, and this type of molecule, which all of them have in common the fact that to pass from one state to the other, there is the involvement of an isomerization, which means that there is a change of the geometry and the volume of the molecule itself, which has important consequences on the speed of this transition. Now, this molecule generally go from a colorless state to a color state when they absorb the light, and recover when the clear state when are in the dark. For this reason, these molecules are already employed in as a photoprotective coating in ophthalmic lenses. Now, these dyes are they have very good properties. They can dissolve very well in polymeric materials. They are commercially available. You have a very broad availability of colors and the kinetics. However, they have some drawbacks, important drawbacks that are limiting some applications. One of these is the chemical stability, and the other one is the slow response in solid material. And this is the property which we were focusing initially in our project. And this is an important property because it's basically preventing the application of photochromic material in other applications where the interconversion between the clear state and the dark state and the other way around must be fast, like in sportswear or automotive sectors. And mainly the process that is affected is the one that goes back from the dark state to the clear state. And this is actually a market need. If you look to some web pages of providers of ophthalmic lenses, you see that they are continuously advertising that they achieved new photochromic back to the initial state in less than 6 minutes, in less than 4 minutes, or even in less than 5 minutes. And this is actually one of the last advertisement that was published last year with a new generation of ophthalmic lenses. So this is a continuous need of achieving a fast photochromic response. However, this has been a scientific challenge because even though the photochromic response can be very fast in a liquid solution, because this isomerization and the conformational changes that are involved in these changes are occur very quickly in a soft material like a liquid. But when you go to the solid crystalline state or in a glassy material, you start having a problem of interaction with the matrix or aggregations, which prevent the actual photochromism. But the most important part for us was the fact that if you take these dyes and you embed them in a polymeric material, you observe that the back process is slowed down a lot compared to what you have in a solution. And this is due to the fact that you have a rigidity that is of the matrix that is preventing the photochrome to recover quickly to the initial state. In the past, several strategies have been developed to solve it. Some of them are based on making new molecules that their structure during the isomerization, so the process can be fast also in a rigid environment. By adding soft functionalities around the molecule, or dissolving the molecule in softer medium, or even in structure where you have a void inside, so the photochrome has a free space to isomerize. So this strategy worked quite well in terms of reducing the isomerization, increasing the isomerization rate, but either had very specific, require several synthetic steps, and very often they deliver opaque material. So these three factors prevent this strategy to be scalable and used in marketable products. So here we came with our encapsulation idea. So if we make a composite of capsules where we have an oil core, like for example, a colorless inert oil with a very high boiling point to provide certain stability to the capsule and immiscible with water, then we can add some photochromic dyes inside the solutions, like for example this. And now we guarantee that the interconversion rate, since it's the dye is in solution, is going to be fast, even if we have a dry solid capsule. Now, to make these capsules, we use a well-known emulsification method, which is based on mixing an aqueous solution containing a surfactant with our oil solution of the photochrome. That's why we need something that is immiscible with water, because we need to create an emulsion. So this is our oil solution with a photochromic dye. Then we emulsify the systems by creating droplets that contain the photochromic dye. And finally, we generate the shell around the capsules. So to generate the shell, we need to put some material that is going to polymerize to generate the final polymer. And this can be added either in the water phase or in the oil phase, depending on the method. These are some of the capsules that we obtain. And in this video, you can see the release of the oil when you apply pressure to the capsules. This indicates that the capsule actually contains the oil solution. Then you can take the suspension, you add the polymeric materials, and you cast it in a surface. You let the solvent evaporate, and you got your final composite. So this is how it looks like, one of the first films that we made. And if you go to a closer inspection on the sides, you can actually see the capsule that are trapped within the polymer, preserving their structure. And inside here, there is the oil solution of the photochromic dye. So if you radiate with these dyes with the UV light, you induce the coloration of the material, so we preserve the photochromic activity. And when you stop the radiation, the material goes back to the initial state. And what is interesting and most important is that the kinetics with which this material goes back to the initial state is overlapping with what you have with the same dye in solution. So basically, we have a solid material that behaves like a liquid solution. Now, these are some quantitative data. If you compare the rate of the photochromic dye with the same photochrome directly dispersed in a polymeric material, we see that the films prepared with the capsules fading back to the clear state with the same speed of the solution, while the one that is made by the photochrome directly dispersed on the film is much slower, even more than one order of magnitude slower than that. Here I got another video that shows how fast the material clear up after irradiating and stopping the photochromic, the light, even if we have a solid powder. After that, we show that this process can be tuned, because we can change the photochromic dye with any commercially available dye that is soluble in our oil, achieving multiple colors. But also we can achieve a fine control of the kinetics by simply changing the oil that is inside the capsules. So we have a very fine control of the optical properties in the solid state without needing any chemical functionalization or modification of the matrix or the dye. So that was good, but we had a main problem, which is the opacity. These films were all opaque, which means that they could not be used for optical applications. So we knew that this was basically caused by the scattering of the capsules because they were of too much large size. So we knew that we needed to do some capsule size reduction. And from here started an industrial development of the product. Also, thanks to the help of Photochromic, which is the company that was created to commercialize this technology after it was licensed to them. So in Photochromic, we managed to reduce the capsule size from the microscale to the nanoscales. And this reduction had a very huge impact on the physical aspect of the film. We passed basically from this opaque film to the highly transparent film. Now, this is still photochromic, and you can change the photochromic dye for all the others, and you always get the same response as in the liquid state. Here I show you another video where it shows the differences between film prepared with our technology with a film prepared with a standard technology, and you will see that it fades much faster than the standard polymers. We also were interested in scale up the process because of the capsule preparation and the films, because for final applications. And we were able to also to integrate these films in laminates, glass laminates or plastic laminates for a final application. And we were also able to prepare a prototype of this material. And now we are investigating this with companies to see if we can get a marketable product in the near future. So that was the first part, and but we knew that we could achieve something more with the capsules. This is not only that, but because going into details of what next, I wanted to give you another hint about photochromism. So until now, I've been speaking about light-induced coloration and discoloration in the dark of the photochrome. This is called positive or direct photochromism. However, this unstable species in some circumstances can be stabilized, and in a way that this is formed without needing irradiation. So this, once you have this, usually in a very polar or acidic environment, when you irradiate this, you induce the re-enclosure of the molecules and the discoloration of this, which now goes back to the initial state when you go in the dark, in the color state. So now you have the opposite process of this, and that's why this is called negative or reverse photochromism. This has an important application because it has absorption in the visible region, and it can find applications as a rewritable devices or new anti-gutter fighting technology. So we wanted to investigate the possibility to make materials that show reverse photochromism. And for this, we decided to use, again, the encapsulation strategy. However, to do that, we needed to substitute the oil that is inside, that I showed you before, that was an inert oil based on, for example, coconut oil derivatives, to something that was interacting and stabilizing the color form of the photochromic dye. So we needed something that was either able to create hydrogen bonding interaction or was doing acid-base reaction with the photochromic dye. So if we were achieving this species in the dark, then we should be able to irradiate with a visible light and induce the discoloration of that. So for that, we use also spiropyrans, which have the characteristics that in the solid, in their open form, they can have two different extreme forms, which are the protonated and the no protonated form, and the equilibrium between them depends on the acidity of the medium. So this photochromic dye is also allowed to give a tuning of the coloration depending on the medium pH. So as a proof of concept, we took this spiropyran molecule and we embedded this in an anoic acid, which is a weak acid. And immediately after dissolving this dye in this liquid, we got as a consequence of the equilibrium between the protonated and non-protonated open form of the dye, which is shown here. Now, if you irradiate this visible light, you induce the discoloration of that, showing reverse photochromism. If you reduce the polarity of the medium and use this dihydroxy-terminated polydimethyl siloxane, you basically generate hydrogen bonding interaction with the dye, and you stabilize the open form without protonation, and therefore you got this color change in the initial state, which again discolor upon irradiation with visible light. On the other hand, if you increase the acidity of the material and you add dodecyl phosphonic acid to the noranoic acid, you induce the protonation of the open form of these dyes and the yellow coloration of that. So basically, also this one can be photochromic, and this means that by using the same dye, we were able to stabilize 3 different colors by simply changing the medium of that. So if we were able to encapsulate this, we should have 3 different capsules, types of capsules with 3 different colors, and this is actually what we got. We managed to get 3 different pigments containing these 3 different mixture and our photochromic material, and each capsules reproduce the color that they had in the bulk solution. So once again, the capsule strategy allowed to transfer the liquid behavior to the solid state. And finally, if all these capsules showed a reverse photochromism and discolor upon irradiation with visible light. And finally, when you put these capsules inside films, you obtain the corresponding color film that upon irradiation with visible light and using a mask, you can get quite good resolution drawings and writings, and then you can erase them and then rewrite again. So these materials could find application as rewritable devices activated by visible light or anti-counterfeiting technology. So to sum up, I showed 2 examples of what we can do with the capsules and to obtain functional materials that behave like a liquid. With this, I would like to acknowledge my research group at the ICNU. The PhD students that have been carrying out this work, and Professor Jordan Nando from the UAB, with whom I got a long collaboration during the last 10 years, and then funding, and of course, for listening.